Hello, good evening. This is Juan Gutierrez. I am submitting the final project uh, assignment for the Machine Learning Foundation Project Manager's course. In this case, we are going to predict the electrical energy output for a combined cycle power plant based on a dataset that was given in the assignment. So here I'm proposing like a roadmap for solution, like from the perspective of a product manager. So basically, we are going to frame the problem. Later, we will run the EDA execution to understand and assess the dataset provided. Later, we will train and conduct the split for the testing and the baseline. We will identify some models and we will evaluate them to determine what is going to be the best model for the result that we want to achieve. And finally, the business interpretation or the conclusion. So basically, we need to decide in this model what is going to support in terms of business perspective, if it's the scheduling, capacity planning, or maintenance. The unit of prediction that we have is 1 hour. What is the target variable, the energy output that is coming out for the target variable we want to predict, and how accurate it's going to be based on the results. So the metric that we're going to use is the RMSE to determine how many megawatts of deviation we have on average. So in the for the EDA execution, I have run and load the dataset in a Python notebook. Basically, here we can see the summary and the description with the basic statistic metrics or results, and also the histogram distribution for each one of the variables that we can find in the dataset. Also the distribution variables and the correlation heat map between each one of the variables and the correlation matrix, just to understand the data fully. So we have a summary for the data set. So we have 9,568 hourly observations, each with the following features. We have temperature, ambient pressure, relative humidity, exhaust vacuum, and the power output. That is the target that we're looking for. Here we can see the units and the range for the data, and also a description of each one of the variables. We can conclude here that the data set is extremely clean. I mean, there are no nulls and major outliers, and is well behaved, so it's perfect for our regression modeling. So based on the points of the assignments or the topics that we need to address, we need to determine what machine learning approach is needed and select an appropriate output metric for this. So for this, we have the type of learning machine learning approach. What we can see is that based on the understanding of my understanding of this is a supervised learning regression model. We have labeled data and the target variable P is continuous. So the approach that we should go for should be supervised regression model to predict a continuous target, that in this case is the net hourly electrical energy output. So the output metric to evaluate performance, I will use the RMSE, as I was mentioning at the beginning, as the main evaluation metric to assess the model performance on predicting net hourly electrical energy output. Why RMSE? Because it measures the average magnitude of prediction error in megabytes in this case, and it penalizes large errors due to squaring, which aligns with the business impact or mispredictions in the power output. Its power is widely used and is well understood for continuous prediction problems. So the second point is determine which possible features we may want to use in the model and identify the different algorithms. So the features, as we mentioned, are the ones that we need to predict the net hourly energy output PE. So the features are the ones provided in the data set: the temperature, the ambient pressure, relative humidity, and the exhaust vacuum.
And based on the learnings of the course, and since it's a project focused on machine learning foundations, a short list for the algorithms to consider will be multiple linear regression and the random forest regressor or gradient boosted trees. I believe that with the results we can compare them using the RMSE and the test set, and discuss the trade-off between interpretation to determine what is the best performance. So I split the data into train and test sets. For this, I split the data set into 80% training set and 20% test set. The test set is held out until the final evaluation to estimate out of sample performance. Here you can see a sample of the code that I use in the Python notebook to perform that. The steps to complete the project, basically I have a validation strategy and to compare the different for comparing the different models. So to compare the different model candidates, I use 5-fold cross-validation of the training set. The cross-validation provides a more reliable estimate of model performance because it evaluates each model across multiple train validation splits, reducing variance caused by single validation set. Since the dataset contains 9,560 rows, cross-validation is fast to compute and provides a robust basis for selecting the best model. The test set, 20% of the data, was kept completely separate and used only for the final performance. Here you can see also a sample of the code. So in the model comparison using cross-validation, the validation strategy recap. To select the best model, I applied 5-fold cross-validation, the training set. Each model was evaluated using RMSE as the main performance metrics, as I already mentioned. So the model 1, multiple linear regression, uses all 4 features. Temperature, ambient pressure, relative excess vacuum, is simple, fast, and interpretable. Serves as a strong baseline for structured datasets like this one. The random forest regressor. So here I can compare the cross-validation results, and here are the results. As you can see, we have a lower RMSE for the random forest. So the random forest, the conclusion is that the random forest achieve a lower cross-validated RSME than the linear regression. Because lower RSME indicates better predictive accuracy, the random forest performed best, and therefore I selected the random forest as my final regressor as my final model. So here you can see the samples of the code in Python, in the Python notebook. And as I mentioned, I compared the two models, and the RSME across all folds indicates a superior performance. Therefore, random forest regressors is selected as the final model. So the final model performance evaluation, the metric, as we mentioned, is the root mean square error. And in this case, the test set the final model achieved at test RMSE, the 3.5 megabytes with the exact value that you can see there on the screen. And you can also see the code for that. And the final interpretation is that an RMSE of around 3.5 megabytes means that on average the model's prediction differ from the actual net hourly electrical energy in about 3.5 3.25 megabytes, given that the plant's output ranges from 420 megawatts to 496 megabytes. A prediction error of 3.5 megabytes corresponds to less than 1% of the total output, and hourly output is influenced by the ambient conditions that vary dynamically. This level of accuracy is highly acceptable and operationally useful. Thanks for your attention.